A very good afternoon to one and all. Last class we have been discussing about digital signature process, right? And how it works, like a general structure of digital signature we just saw. That is, you'll be using two algorithms called signing algorithm at the transmitter end and a verifying algorithm at the receiver end, right? So actually, this digital signature process is also going to work along with the key also. That is, in order to make it more sophisticated and more reliable, okay, they started adding keys. So how the keys are going to be used in digital signature process in a sense, it is going to make use of the same public key system which we just discussed in our module 3, like how we had a public key and a private key, right? So not in module 3, yes, it's in module 4, right? And that is, every user will be encrypting using public key and the receiver will decrypt using his private key. But here there's a small difference in the digital signature process. So what the process will do in a sense, in the signing algorithm, the transmitter will use his private key. That is, Alice means Alice will use his private key to sign the algorithm. Okay, and you'll get a signature as output. Once this message and signature copy has been sent to the receiver will apply his verifying algorithm over this message and signature using Alice's public key, that is transmitter's public key. So it's a vice versa. If you take a cryptographic system, generally in cryptography, if you take transmitter will encrypt using the public key and the receiver will decrypt using private key. Right. Whereas if we come to digital signature part, here the signing will be done by private key and verifying will be done by public key. That's the difference here.
So,
Yes.
but public key will be available for everyone. So, what's like anyone can decrypt it, right?
No, actually here we are not doing the process of encryption decryption. Here we are just signing the part. Actually, this has nothing to do with the encryption part. Sometimes they won't encrypt the message also, and they will send. The digital signature is going to ensure only the data integrity part. It's not going to ensure you the data confidentiality part. Data confidentiality will be taken care by the encryption part. For example, as I said, so I don't want to reveal my data means you won't give the message as an input here. You'll encrypt the message and you'll give the ciphertext as an input here. So at the receiver end, first the ciphertext will be decrypted to plain text, then they will verify it with the verifying algorithm. So in this process, we are just
So my
saying
doubt
only,
is,
yeah.
so if the key is public, then anyone can copy that uh, let's say whatever message you're sending, anyone can
Okay.
decrypt it and fabricate that message, right?
Yeah, I mean, it's
Fabricate the
suppose
signature.
fabricate the signature, it's not possible because here signing algorithm will be different, verifying algorithm will be different, and signing the signature which you got is obtained by using signing algorithm and the private key. So a person who is going to get the value of the signature, he can't able to retrieve it back using the public key here. The algorithm will be designed in such a way that without the knowledge of private key and without the knowledge of signing algorithm or without the knowledge of verifying algorithm, simply having the public key alone, he can't able to retrieve back. Actually, here we are
Okay,
not
so
only
both
discussing.
will know. So
Yes,
both will know the signing and verifying algorithm.
yes.
Okay, sir.
Like how we have, for example, if I take AES means AES encryption process will be known to Alice and AES decryption process will be known to Bob. Like that, if you take any of the digital signature algorithm, the signing algorithm part will be known to the transmitter and verifying algorithm part will be known to the receiver. We'll see some sample algorithms. Actually, here this is nothing to do with any part of encryption. How we had hashing, which took care about only the change in data. The same way, it is application of hashing algorithm. Here giving authenticity that Alice is sending his own message by signing. No one is replicating a data kind of thing. Only that confidentiality can be, sorry, only that authenticity can be given by digital signature, not how we are going to hide your data. It's like, for example, you are, okay, how can we say? Like, okay, you're publishing a paper at that time, you'll be submitting a copyright form. Okay, The copyright form will have certain things. The form will be known to everyone. Here you'll be placing a signature, right? The signature should be legitimate. That's the only concern. My concern is not about who is going to read this thing or nothing. If anyone want to change means, then it's not possible, because if he change, he has to affix the signature again. Okay, this signature can't be replicated. That's the part we are going to discuss here. Is it clear? I think you will get a clear picture if you discuss different algorithms and digital signatures. Is it clear so far?
Yes, sir.
Yes. As I said, the crypto system will be using private key and public key of the receiver, whereas in digital signature process, you'll be using a private and public keys of the sender. Okay. So there's no other process of this one. Like instead of directly signing the message, okay, I can able to sign the hash value alone, because hash value is going to maintain the data integrity for me. So in this application, I'm not concerned about the secrecy of my data. Anyone can able to read the data. That's my application. But the only condition is nothing is that no one is allowed to change the data, but everyone is allowed to view the data. Right. So for this, I'm hashing this message, so which I'll be getting h of m here. Okay, in order to protect this HM value, right? I'm going to send. I'm going to sign it using my private key, and I'm going to transmit the signature and the message. Okay. At the receiver end, again the message will be hashed, and you will be verified using verifying algorithm and the public key. Thereby, this output of the verification algorithm should match with uh, the signature which you have received here. This yes value should match with the verification algorithm's output. If it is verified, then this message will be accepted. Otherwise, it will be discarded by Bob. Right. That is, in this case, they just they're signing only the hash value alone. They're not signing the entire message. Is it clear, guys? Up to this one, if it is clear, raise your hand. If anyone have any doubts, you can ask me now. Right. We see a few attacks on digital signature part. Okay, there are two different ways of attacks. That is called attack and forgery. Okay, attack is different and forgery is different. Forgery will be done by the person who is having some few data about the entire process. Attack will be done by entirely third person. Right. So attacks are, we can able to classify under three categories called key only attack, known message attack, and chosen message attack. So key only attack means, as Arun said, sir, if anyone knows the public verification key, they can able to break the algorithm. Right. This can be done if your algorithm is very weak or it has any very weak mathematical loopholes. Right. In that cases, they can make use of the public verification key to make the attack. In second one, known message attack, okay, the attacker will have valid signatures with him. What is that? Is he got the valid signatures of variety of messages. Okay, that is, for assume there is a transmitter T. Okay, it's just going to send a receiver, and we have attacker. Okay, he has the knowledge what are the data present here. Okay, starting from D1, D2, and goes on up to DN. Okay, n number of data packets are there, and he also have different signatures in the box, but he doesn't know which signature matches with which document. Okay, he has valid signatures with it and variety of messages, but he don't know which one to match. So at that time, he'll be keep on trying with all the conversations to make them attack. So you have to keep these things to be confidential before transmitting. Then comes a chosen message attack. So here the attacker will first learn the signatures of many arbitrary messages. Okay, using that one, he will try to only sneak peek only to particular message which he needs. Okay. Then comes the forgery types. There are two types called existential forgery and selective forgery. In existential forgery, what they will do in the sense, the attacker or the person who is going to forge will create a pair called message signature pair. Okay, M comma sigma, where sigma is not the original signature, but he will have created another signature which exactly matches with the message here. Okay. Selective forgery attack, what he will do is he will already chosen a particular message. He won't to target all the message on the thing, but he would have already chosen the message prior to the attack, then for that particular message, he will create a legitimate signature. Whereas in this case, he can choose any message and he can able to perform the forgery. This is only a selective forgery, this is existential forgery. Now we move to the main part of digital signature, which is nothing but one of the trending digital signature schemes which have been in use. And you can able to see from the names, all these digital signature schemes have been evolved after the cryptographic technique came into existence. Every digital signature scheme has a touch of a cryptographic algorithm inside them. Right. Some famous are RSA based digital signature scheme, then ElGamal and Schnorr digital signature scheme. Schnorr is also an encryption algorithm which we didn't study because it is not in our syllabus, but we discussed this one digital signature scheme. Then the famous digital signature standard, which is nowadays mostly used in all our banking transactions and all the digital money transactions. They make use of DSS. Then our elliptic curve digital signature scheme, how like add-on will help us to reduce the computation complexity. We'll see one by one. Okay, don't worry. In this module, the entire module will be coming out as a theory part only for your examinations in your FAT exam. We won't have 6 module for your CAT 2. So we'll be having only theory part. So just go with the flow and try to understand the concepts of each and every digital signature scheme. If you have any doubts, you can ask me then and there. So now we start with the RSA based digital signature scheme. So this is a general idea, a general outline of how the entire process in RSA based DSS, that is digital signature scheme, works on. So we have a message called M and the signature is S, okay, and E comma N is a public key and D is a private key. Right, the same notations which are used in our RSA encryption system. Right, and there's a function called F which will be used at the signing. And here you can able to see in RSA digital signature scheme, the same function F is used for verification also. The only thing is nothing but the input varies. The same function is used. Okay. Can you people able to spot there is a mistake in this block diagram? Actually, it's a mistake in the book also. Can you people able to tell me what is a mistake here in the block diagram? Anyone able to spot it? Just check the inputs, outputs, other things, whether everything is fine. If you're able to spot, you can unmute and tell, or you can use your chat box. That's a huge blunder made in the book, that's why. Only in RSA based, that in this block diagram alone. Anyone? Not able to find? Actually speaking, your digital signature scheme, we will be using signing process with the help of only private keys, not in the public key. In this place, actually D should come here, and in this place E should come. Right, because D is a private key here and E is a public key for RS. Right. So for signing, I'll be using the message, I'll be using the private key, and this is also known. Use it for the model operation. At the receiver end, for the verification, the signature will be taken, and along with it, I'm going to take the public key value and the value of M. Okay. And the output here should be matched with the, for example, you're getting M dash as output. Both should be matching, then only the data will be accepted. Right. So I'm not going to discuss again the key generation process, like how the values of E, D, and N are going to be generated. Same thing, whatever we just saw with the RSA algorithm. We'll be choosing two prime numbers, so multiplication will give me N, then you will be choosing phi of N, then you will be choosing E, then you will be generating D, which is nothing but a multiplicative inverse of E, and so on. Right. Now we'll see this how the signing and verifying process is going to happen in this RSA based digital signature scheme. So I got the message here. M is risen to the power D, which is a private key. Okay. Modulo N. gives me the signature. So in this case, they are transmitting the message without any encryption directly. So they don't worry about the confidentiality of message here. So at the receiver end, assuming that the message and signature are transmitted without any loss, it is received here. And here the verification algorithm, it's both are using the same function, that is exponential function. But only thing is something, but here the inputs are going to vary. Here message is given as input, here signature is going to be given as input, which will be risen to the power E, that is a public key value under modulo n, and which will be giving me m dash. So now both are same means then it will be accepted. And this is a basic, very basic, the same RSA based scheme is used here. Like, is it clear guys? This one, we'll see one example so that you'll get a clear picture. Right. So here this is how it will work on, right? I hope you remember how RSA works. We'll be getting a value of P, Q. We'll be finding the value of N by multiplying both of them. Then you'll be generating phi of N, right? And you'll be finding E. You will choosing E. You won't be finding, you can choose the value of E here. Then you will be calculating D such that D will be equal to E inverse mod phi of N. I hope you remember. Right. And we'll be getting this one. Then suppose if message is 19070, then he'll be using his private key exponent to sign this message, so that you'll be getting a signature value as 210625 and or something. Okay, once the message and the signature is sent, we need only the signature part, right? This is the S which we got, and here they raise the S to the power of public value E, which is 313, which I have chosen the previous slide, and we got this same answer 919070. So M and M dash going to match, so it is verified. Right. This is how your RSA based scheme works. Anyone have any doubts in this part? If it is clear, raise your hand. If you have doubts, kindly unmute us. Same, nothing different. Only they are using the same RSA based schemes. Okay. Sometimes we can not to make the system. For example, assume that your message is running with n number of bits, very big number. So at that time, if I want to sign, then the computation will be high. But you are making a trade-off. That is, instead of making the signing process tedious, you are introducing hashing part here. That is, you are hashed your message for whatever the length of the message may be. For example, you are going with MD4, you are going to get only hash value of 128 bit. Okay. Now this digest value is taken and it is signed here. So at the receiver end, once the message is received, they are hashing and they are comparing only the digest value here. They are not comparing the message value because they are signing only the digest here. So here they are verifying the digest value alone. If digest value is same, then obviously there's no change in the message, so it will be accepted again. There's another way where you can able to apply your RSA based scheme on digest. Right. So as I said, when digest is signed instead of message itself means, then you are making the system to be more robust based on the strength of the hashing algorithm. Okay. How we move on to next one. So this one will be somewhat different. Okay. Here again, this is a ElGamal based digital signature scheme. If you remember properly, in ElGamal crypto system, we created two ciphertext, right? C1, C2. Like that, in the place of two ciphertext here, and I'm going to use two signatures S1, S2, and we are using the same notation D for private key, and we are creating two public keys E1, E2, okay. And the random secret. If you remember properly, the unique feature of ElGamal system, random secret known only to transmitter. Here also this is a secret used as transmitter end alone and the message. This is a general structure. Here we are using three functions, three different functions for signing and verifying. F1 is used for creating signature S1. F2 is used to create signature S2. Right. And here we are using the same function F1 here to create one value of verification value. And another function called F3 is going to create me another value called V dash. This both has to match. And here this first function will take input of the public key value E1, the random secret R, and the public value known to everyone P. So this will give me a signature S1. and this S1 will be given as input for my second function here. So this is actually the original signaturing process going to happen, where your message is given, the private key is placed here, because people used to ask, so you said private key will be used for the signing, but here you are using public key. But here only the actual message is involved, the actual signing process is going to happen. So here the private key comes, the random secret is again pressed here, and the public value and the signature S1. So, but here in this case, the modulo is P minus 1. It's not simply P, it's P minus 1 to get the signature S2. And this S1 and S2 is going to be used here along with the public key value E2 and P. And E1 message and P will be used to create the another value called V, and this is V dash. It is the general process, and the key generation process I'm going to skip because same process I don't want to repeat. I'll just explain how this part is going to happen. You will see an example. At that time, I want you people to work it out certain things. I will let you know, just work it out and let me know the answers. Okay. So here I'm going to use the private key D and the random secret R with the signing process. This is your function F1 and this is your function F2. And you can able to see this F1 is again your same exponentiation, and this is your F3. Right. F1 E1 power R mod P. So you have all these values, public values with me and the random secret. This part, okay, since in our public key crypto system, all the things will be in terms of integers. So this is a conventional subtraction here. That is message M minus D times S1. This part R whole inverse is nothing but the multiplicative inverse. Under modulo P minus 1, you have to find, then you have to multiply this with the value to get the signature S2. So S1, S2 and message M is transmitted to the receiver N, and we are using same function here to create the first verification value V1, and V2 they are using E2 power S1, S1 power S2 modulo P to get my second verification value V2. Right, both are same, then it will be accepted here. Okay. So I hope it is clear, right? Before moving to example, whatever we just said now, is it, if it is clear, can you raise your hand? Okay. Now Alice has chosen the value of P, the largest one of the prime numbers, to be this one, and E1 is this one, and D is this one. Can you people able to tell me the value of E2? E2 is nothing but E1 power T mod P. I hope you remember in ElGamal system. So now I want you people to tell me the value for E2 in the chat box. So it's quite big number. Okay, you can use any method of your wish. You can use, that is, you have to compute 2 power 127, the maximum computational power of a calculator you can choose. Then you can do this in a splitted way. I hope everyone knows how to find it. Can you tell me the answer for E2 in the chat box? Ashish, you're getting 1702. Okay, we'll see. Actually, it's a 4-digit output only. Okay. People are getting the same output. Can you put a thumbs up button to Kashish answer? Or you can post your whatever answer you're going to get. Only Kashish solved. What about others?
Excuse me, sir.
Yes, yes.
For this, we can use calculator, right? Like, don't have to
Yes,
show
yes,
the
yes.
working.
No need to show. No need to show, because
Okay.
if you want to show this one separately, mostly you have to go with our square and multiply method. It's a separate 10 mark. So actually in examination, we, if I mean mostly if these questions will be arising in our ElGamal crypto system. At that time, for key generation process, no need to show these things.
Okay, sir.
If I want you people to specifically show some calculations, I would have mentioned in the question paper. Like for example, calculate the multiplicative inverse using so and so method. Means at that method you should have calculated and shown. Otherwise, no need to show everything.
Okay, sir.
So you got 1702, right? Now they chosen the random secret to be 307, and they are announcing the values. Okay. Now they want to send a message. So here the message M is 320, and they're creating the signature S1 is E1 power R mod P actually. So 2 power 307 mod 3119 will give me 208. This is signature S1, and S2 M minus, this is M minus D times, okay, D is 127 here, the S1 value. So once they multiply, actually here you will be getting a negative value. Can anyone tell? I hope everyone knows how to convert a negative into a non-negative value. So you will be finding a multiplicative inverse. Here obviously you'll be getting some negative value. Okay, assume this is like minus A, multiply with some 307 inverse mod 3118. So at last you'll be converting them into positive value. So this is the signature S2. So at the verification end, you will be getting the message and the signatures S1, S2, and they will be calculating V1. V1 is E1 power mod, is E1 power M mod P. So I'll be getting 3006. And if you apply the same thing with the second algorithm, that is for verification value 2, D risen to power S1, multiply with the S1 risen to power S2. Actually, here the mod P is common to everyone, so they just left it. So at last, you'll be getting 3006, the same thing. Now the signatures are verified here. Actually speaking, this in real time it won't be such a simple thing. It will run for many digits, right? And one more thing.
Excuse me, sir.
Yeah, yes, yes.
In that case, what was V1 and V2?
Actually, V1 and V2 are nothing but the two verification values. Actually, if you see RSA, they took the message itself as a verification value there. So here they want to, I mean, here they are creating two values. The two values should come same. That is, I'll just go here 1 second. Yeah. This value V1 is built from the message here, and V2 is built from the signatures here. So using these two, they're creating two verification values, like a temporary values, both has to be same. Whereas if we go with our RSA based algorithm, here the message which is itself directly used as a verification value here. That is M is equal to your V2 here, and this M dash is nothing but your V1. So here is V1 is created from the signature and M is directly used here. Whereas in our ElGamal based system, V1 is based upon this M and V2 is based upon the signatures. That's all. That's a simple process. Yeah. Instead of directly using the messages, they are manipulating and creating values here.
Okay, sir.
For now, in this case, for example, now Alice want to send another message because as per digital signature, each document should have different signatures, right? For example, I'm sending D1 document D1, which is the previous message is 320, I think so, right? We got a different signature, right? And now I'm sending second document, which is going to carry the message is 3000. For this, I have to get different. This is S1. I mean, this is okay. Signature is yes, means this is yes star. This is another signature I have to get. So whether I have to create all the keys to be totally different? No. Okay, for making another attempt of transmitting the message to the same person, Alice will only change the value of R alone. That is his personal secret alone, he will be changing. In this previous thing, the secret value is chosen to be 307. In this case, he's changed the 307 to 107. So, and he is using the same method. The message is here. Since he has changed the value of R, here the entire value of S1 changes. Once S1 changes, this S1 impact will be here, and the message is going to be different. And same value of D is used 127, and same value of P is also used. At last, I'm getting 2526. Actually speaking, this is this is correct actually 318 because P minus 1. Second function uses P minus 1, so 3118. Right. And verification value I mean, can you able to see there are two different signatures. Here I'm getting 2526 and 2732. Previous one I'm getting 2083 and 2105. The message and the random secret is alone varying here. And they created a verification value which matches. So as per ElGamal is concerned, if you want to retransmit data to again to the same receiver or anything, only change the value of R alone. No need to generate the values of E1, E2 again. Right. So is it clear, guys, up to this ElGamal process? If it is clear, can you raise your hand? If you have any doubts in any part, you can ask me. Right. Okay then. Okay. So I think with this we'll wrap up today's session. Actually, we are going very far ahead. So we'll go a little bit slow. Once completed, we'll have discussion of refreshing other stuffs. Okay. So with this, we'll wrap up today's session, guys. Thank you.